Alright, in our last video we met 3 discrete random variables which we described as these magic boxes. You can reach into a box and ask it for a number, and it'll quickly run some experiment and hand you some result. So X was the easiest one. It would simply roll a die and tell you what it got. Y would roll 2 dice and tell you how many 6s he got, but remember, he wouldn't actually have to tell you the values of the 2 dice. Right? He'd just tell you how many 6s he got. Z would roll a die over and over again, aiming to hit a 6, and after he eventually hits it, he counts how many times he failed before succeeding and reports that number of failures to you. We briefly mentioned the set of all possible outcomes for each of these random variables, which in probability language, remember, is known as a sample space. Okay, it will still be called a sample space, but we'll see soon. It's got some very interesting jobs now. So for X, the plain die roll, the sample space, it's just the numbers from 1 to 6. For Y, it was just 0, 1, and 2. That's how many 6s he could get. And we saw for Z, it could be any non-negative whole number. Right? We saw that he could give you a 0 if he hit the 6 immediately, or if he's super unlucky, he could take 100 tries or 1,000 tries before getting a 6. Okay, but it's technically possible, so that means that Z's sample space is really any non-negative whole number. Now, these outcomes are not equally likely in Y and Z's case, right? And we saw that a bit last time as well. So say with Y, he's much more likely to end up handing you a 0 than to hand you a 2, since getting no 6s when he rolls 2 dice is far more likely than getting 2 6s in a row. Right. The aim of today's video is to make this precise, to calculate these probabilities, and along the way to introduce the related language and notation. So we'll start with Y, with his possible outcomes of 0, 1, and 2. Now, what does it mean for him to give you a 0? Well, it means he must have gotten no 6s, so he missed 6 on both his rolls. Missing 6 happens with probability 5 out of 6. Then it's got to happen again, so we multiply by another 5 out of 6. This gives a probability of 25 out of 36, so we can write that down as the probability that Y equals 0. Okay, and remember, when we say Y equals 0, we really mean reach into the Y box, he gives you 0. Okay, now what would it mean for him to give you a 1? It means, well, he must have gotten exactly 1 6. So either he missed the 6 on the first roll, then hit it on the second, or the other way around. So he hit the 6 on the first roll and missed on the second. Okay. Now again, to miss the 6 happens with probability 5 out of 6. Okay. And then means you multiply. And hitting the 6 happens with probability 1 out of 6. Okay. Now the other way around must be the same by symmetry. I mean, for the 2 die rolls, neither of them is more or less likely to be a 6. It's just the same. So by symmetry, those fractions would be the same, just appear in reverse order or something. But of course, the probability of the same thing happening in reverse must be the same. And so that means we just got to multiply this number by 2 to account for the fact that the 6 could be first or second. Okay, this gives us 10 out of 36, which I'll leave unsimplified for now, you'll see why soon. So we'll put that there as the probability that Y equals 1. Okay, finally, for him to give you a 2 means he hits the 6 on both his rolls, the lucky fella. So he hits a 6 with probability 1 out of 6, then it's got to happen again, so we multiply by another 1 out of 6. And this gives a probability of 1 out of 36. So we can write that down as the probability that Y equals 2. Now here's the interesting thing. If we see these green numbers here, let's see these green and pink numbers as sets, right? What we've just done is define a bunch of arrows, or some kind of relationship between these sets. And I wonder if that's a familiar sort of picture to you, right? Hopefully it rings a bell from an earlier topic, because this is exactly what a function is, right? So we've actually defined a function by working out the probabilities of each of those outcomes. So we can see these green numbers, the sample space, right, as the domain of a function. right? How do you define this function? Well, if you give this function some outcome you're interested in, it spits out the probability of getting that outcome. Okay. Now, normally we use a letter f, just like any other function, and we might have to label and subscript the f with a random variable's name, but for some strange reason your textbook likes to use little p for that instead, so I'll follow suit. I guess it stands for probability. We'll go with that for now. Okay, so again, you give the function some particular outcome. Let's say there's 0. Right? Then p of 0, the function applied to the value 0, would be the probability of getting that 0. Right? And so it will be the probability that the y magic box hands you 0, which we calculated to be 25 out of 36. Likewise, p of 1 would be the probability he gives you 1, which we saw was 10 out of 36. And p of 2 would be the probability he gives you 2, which we saw was 1 out of 36. Okay? This sort of function defines what we call a probability distribution. Okay, and because it's a discrete random variable, we might call this a discrete probability distribution. Okay, and for discrete probability distributions, we call the function a probability mass function. Okay. Alright, and here's why we didn't simplify the 10 out of 36 earlier. We can clearly see that adding up these probabilities gives a total of 36 out of 36, which of course is just 1. Okay, that must be true not just in this case, but for any probability distribution and any random variable. It's just the fact that probabilities of every possible outcome must add up to 100% in total, or just the number 1. Okay, and so that's what makes it a probability distribution, not some random function. Okay, so I hope it's really just familiar stuff you've seen before. These probability calculations, hopefully you're quite familiar with, but now we're just sort of formalizing and expressing these things as a function, which will be very convenient for what we do later. Okay, alright, so let's go back to x now, the plain die roll. His possible outcomes are the numbers from 1 to 6. No calculations need to be done here. The probabilities are all, of course, just 1 out of 6. Okay, but again, we can see this as a function rather than, list all the probabilities. We can sort of just say, cheat a little bit, and just say for every little x belonging to this domain. So whether this little green x is 1, 2, 3, 4, 5, or 6, then p of x, which is the probability of getting that outcome, is 1 out of 6. Right. Another way we can write this function in more old school probability language is big P, which just means probability of, probability of what? Well, that when you reach into the big X magic box, so this big blue X here, then no matter which particular outcome you're after, whether it's 1, 2, 3, 4, 5, or 6, right? That's what the little green X represents. Then the probability is 1 out of 6. Okay, I know at this point normally the notation gets really weird, right? I know that the language might be confusing, especially because there's big P's and little p's and big X's and now little X's, where'd they come from? So let's go over both of those statements again. Okay, the little p is just a function. You give it a particular outcome you're after, say any number from 1 to 6, and it gives you the probability of getting that outcome. So for a fair die, like in X's case, it'll just give you the fraction 1 out of 6 every single time. Okay, the big P bracket big X equals little x, okay, means literally the same thing. Actually the same thing, just different way of writing the exact same thing, okay? There's no difference whatsoever between P bracket big X equals little x and just saying little p of x. Same thing, okay? Okay. It's just more helpful to write it this way when we're dealing maybe with a few different random variables at the same time, maybe, because it's not clear what little p applies to then, okay? Alright, the big P is notation you've used for the last couple of years. It's just the way of asking for the probability of something. Okay, now the event we're after is that, well, what's the inside of the bracket? Big X equals little x. What does that mean? What's the difference between big X and little x? That's what question we often get. Right? Remember, big X is not a number. Big X is a magic box that you reach into and you grab numbers from. Right? Little x, on the other hand, is a particular number that you could end up with when you do that. So little x, right, is a particular value, like 1 or 2 or 3 or 4 or 5 or 6. Big X is the magic box that you're grabbing all these numbers from. Okay, so by writing P of big X equals little x, we're saying what's the chance that when you reach into the big X magic box, it hands you whatever little x is as a result. Okay, then for this very simple random variable, no matter what little x is, right, whether it's 1, 2, 3, 4, 5, or 6, the probability that the big X magic box gives you that number is going to be 1 out of 6. Okay, now you might need to sort of go through that a few times, but I'm sure you get used to it. Okay, so let's look at the last random variable, z. Might make things just a little bit clearer, maybe, hopefully. Okay, and this z guy could give you any non-negative whole number. So again, what does 0 mean? Well, 0 means he didn't fail at all, which means he must have hit the 6 on the first try. Now that happens with probability 1 out of 6, so that's going to be the chance that z equals 0. Okay. What about 1? 1 means he failed exactly once, so he must have missed the 6 on the first try, then hit it on the second try. Missing the 6 has probability 5 out of 6, and then hitting the 6 has probability 1 out of 6. Okay, and when we multiply these, you can get a fraction, but we'll write this probability as just 5 out of 6 square. Okay, and you'll see why soon. What about the 2? Well, 2 means he failed twice, so he must have missed the 6 on the first 2 rolls and then hit it on the third. Missing the 6 twice means we square that probability of 5 out of 6 as we did before, okay? And then hitting the 6 again has probability 1 out of 6, okay? And when we multiply those, we can write this as 5 square out of 6 cubed. Okay, hopefully you can see why we're writing it this way, because the pattern is going to continue. So the next one's going to be 5 cubed over 6 to the 4, then 5 to the 4 over 6 to the 5, and so on. Okay, now how do we write this as a function? Right, we can't possibly list all the probabilities, one by one, because there are infinitely many of them, right? But like most functions you've dealt with, you don't define the function by listing every single value. You can define it by finding a pattern and writing an equation, like a rule for the function. Okay, so if given any non-negative whole number, little x is back again, what would p of little x be? Okay, so you can probably just see the pattern and write the answer, but let's talk through the probabilities again just so we're clear. To reach into the z box and end up getting little x, whatever that guy is, might be 10, might be 20, might be a million, okay, he must have failed to hit the 6 x times, and then succeeded in hitting the 6 on the very next roll. That means he missed x times, with probability 5 out of 6 each time, so the end result would be 5 out of 6 all raised to the power of x. Then you've got to hit the 6 on the next roll, probability 1 out of 6. Okay, and that gives the fraction 5 to the x out of 6 to the x plus 1. And once again, we can write this as big P of big Z equals little x to say the exact same thing. When you reach into the big Z magic box and grab a number, the probability that he hands you the number little x, whether that little x is 0 or 1 or 2 or 5 or 10 billion, is given by that fraction 5 to the x over 6 to the x plus 1. Okay, so that's how we define and write probability distributions. Okay, I know the notation might be a bit confusing, so as always, rewatch as necessary, and feel free to ask questions at any time. Thanks for watching. I'll see you around.